Thanks for the invitation to give this talk. This is a pleasure to be able to listen to some of your great talks. During the day, I will have to go back to Lyon tonight, so I'm very sorry I will miss a lot of very, very nice talks. I will try to catch up by reading the papers, of course. There would be a lot of work, but this is the duty of doing this sort of job. Okay, so the goal of this talk is mainly to speak about a theorem of Neuberger, which can prove to be useful in the study of statistical models in machine learning, and which is able to deal with nonlinear situations in order to prove generalization bounds. So I will try to give an introduction about how overparametrized models can be useful in machine learning, which is something that you all know, of course. And then I will try to address some more technical issues in the linear model and then in the deep learning setting. So what we are all interested in is to find a function from an input to an output, and we would like this function to have good prediction performance. For instance, we often use a test set in order to try and assess the quality of the function we've estimated. And of course, this is very useful for an enormous amount of tasks. Well, image recognition is one of them, but as you know, we are facing an enormous amount of applications for which deep learning, for example, could be very useful. Of course, there's been decades of research efforts in statistical machine learning to try and develop methods to find this kind of estimator and efficiently and prove statistical guarantees about them. So what exists, of course, is already very useful from linear kernel methods, tree-based methods, non-parametric regression. So all these tools are very important, and we have to teach them because they form the foundation of classical machine learning, and they give a lot of hints about what's provable and what's not. They also work very well in practice for a lot of tasks we have to perform with real data, for example. But of course, what we're interested in at the moment is also this kind of function, which we call a deep neural network. When the matrices W in this model have a specific form, then you have a specific architecture, and this is a very flexible way of representing functions. So we have a lot of results about this kind of functions, about this kind of class of functions, concerning optimization, of course, also approximation guarantees, and generalization bounds are computable in certain settings. So why such models? Of course, you all know that providing models which have a lot of layers is also a clever way of addressing the problem of capturing features at different scales, as is done in convolutional neural networks. And so this has proved a very, very interesting idea. Now we are using also these kind of techniques to perform amazing tasks, such as producing images based on texts, for example. So this is something which is really fascinating at the moment. I would not like to see how the pupils in high schools will use that when we switch to videos, for example, when we can sort of create nasty things against other pupils. So this is a bit frightening, but as long as we produce such kind of images, it's really fun. Of course, over the last 7 years, there's been a lot of stuff, but this is an old table, and this is just showing that the number of parameters has been exploding in the different, in successive architectures that have been proposed in the literature. And we all know that overparametrization is sometimes helpful. So why does it work? Of course, it works because we have a lot of data and we have a lot of computing power. But this is not enough. And there must be something interesting going on that explains the generalization properties, capabilities of such architectures. So, of course, when we have very overparametrized systems, what we expect is that there's going to be some overfitting, and this is not what we observe in practice for a lot of different architectures that are trained on huge data sets. So this is a mystery, and also non-convexity should be a problem, but when we optimize, when we try to train deep neural networks, it doesn't seem to be a problem, and stochastic gradient descent provides good minimizers of the empirical risk very often. So a lot remains to be understood, and this is the kind of workshop where we can actually learn a lot about these things. So this is really fascinating, and there is a lot to discover, I guess, yet. So why overparameterize? Because we know that there are some pitfalls behind this idea. So there are some very interesting results that can make us understand that this is very important. So we know that overparameterization can capture different features at different scales. We know also that by having very highly parameterized models, we can model things in a continuous limit and obtain, well, using PDE tools, we can obtain very nice results as well. We can also prove that such networks may enjoy connectivity properties that are the type that allow to imagine that there are some paths from stationary points to stationary points that keep the level of the function at a very small altitude, say the worst plus epsilon, depending on the size of the network. So such connectivity results maybe are interesting because they might provide a hint of the fact that all the minimizers are well connected, and there might be something that helps algorithms to find them, because a lot of them are equivalent. This is very interesting. But in practice, of course, you may run into interesting issues. For instance, when the layers are not wide enough, of course, you cannot use those results, those theorems, and of course, the situation gets a bit more complicated. Okay, so we would like to find conditions under which we can still prove generalization. So let's now turn into something very interesting, which is a property of stochastic gradients, which is very famous. It's called implicit bias. And I will not drill into this for too long, but as you know, the gradient descent method is very interesting. We've been applying it to such estimation problems without limit, and so it proved to have very good capabilities when the things are taken as in a stochastic regime, because you can explore the parameter space, and it has been proved, for example, that the probability of reaching flat minimizers increases as you increase the noise of these gradients, for example. So this is a very simple thing, which is, of course, very useful, as we learned from the previous talk. But there is something which is a bit striking, which is that when you have multiple minimizers, of course, the value converges, but also under certain assumptions, the algorithm converges. to some point in the set of minimizers, and in many setups, the algorithm converges to the minimum L2 norm solution of this empirical risk minimization problem. So that means that when you run a stochastic gradient descent algorithm, the solution you're producing has certain interesting properties that should be leveraged in order to understand the generalization of your system. So a simple analysis that is very nicely presented in Francis's book. I don't know when you will publish it. Soon, okay. So this is a great book to read. You have a lot of material which is very nicely presented, and of course you have this very nice analysis of the linear model in the setting where the
this is from another paper, okay?
From?
It's from a paper by Hassi, somebody else, and somebody else.
Tifshirani, Rosset. Okay. So. So I'm not allowed to make some advertisement for your book?
You're allowed. Thank you very much, but it's just like...
Okay, so this phenomenon has been discovered, which is called double descent. Although in this setup you don't have a first descent, it's not a U-shape, but it really depends on how you define your model in order to be able to prove these formulas. But what it shows is that you can overparameterize even in the linear model and under certain assumptions, and using the least norm estimator, then you can prove that this phenomenon is occurring that shows that overparameterization may not lead to something completely absurd. So I will try to advertise for another approach which I developed with Emmanuel Caron from the University of Avignon, which aims at attacking the problem in a different way, and which can be useful in nonlinear setups. So the mathematical model is this. So you have observations y that are a function of the inputs xi plus noise, and we'll assume that the observations are random and IID, and we'll make some more assumptions later on in a coming slide. So the goal is to estimate f star from the observations, and oops, don't read the last slide. So of course what we want to minimize is the expected loss, and we don't have access to this, so you can make assumptions about this loss, such as, of course, it's equal to 0 when the two terms are equal, and we can make the assumption that, of course, it can be strictly convex, twice continuously differentiable, and non-negative. What you do in practice is that you replace this by the empirical risk, which is this, and you try and find the empirical risk minimizer, which is a solution of this. Okay, so we can start with rich functions, which are of this type. So it's a single index model. You try and estimate the vector theta. Here we have a model with a theta star, and you assume that f is a function that is increasing and has certain properties. So these are definitions of sub-Gaussianity and sub-Gaussian random vectors that you all know, I guess. So we'll assume that the data are isotropic in sub-Gaussian vectors, that the matrix is full rank with priority 1, that the covariance matrix is the identity, and of course you can recover all sorts of different settings by just taking transformations. And you have L2 norm equal to square root of p, which is also an assumption that we can weaken if we want to work a little bit more on this. And of course, we'll also assume that the errors are sub-Gaussian. We'll assume also that the second derivative is equal to is bounded by a constant in order for this to work. And this is a kind of theorem that you can get. So in the overparameterized setting, so if you assume that p is larger than a constant times n, here is the radius, and so you assume that you have a constant on the derivative, and if you assume that you have this inequality that holds, which is trivial in the linear case, so that means when f is linear here, then you can prove that with very high probability, your estimator of least norm is no. There exists an estimator, sorry, in this radius of the truth. Okay. So how do you do that? This is somehow easy if you use this result by Neuberger. So it's a very interesting, very easy to read paper. As you see, maybe you recognize the style of the American Mathematical Monthly. So it's a paper that our students can read even in the morning, and it addresses the problem of solving this type of equation. So it's a zero finding problem that is addressed here, and it shows that by running a continuous Newton method, then you can easily prove bounds between the initial, the starting point of the Newton method and where it lands when it solves the problem of finding a zero of that function. So this is very powerful because imagine that in any statistical model, you define an estimator by a set of equations, and you start from the truth. You start from f star, and then you run this Newton method. So it's only conceptual. You don't do it in practice. Okay, but you use the method by Neuberger. Then it will give you a bound between the truth and your estimator using very easy tools. Okay, so how does it work? So Neuberger's theorem is this: you consider that function, and you want a zero of that function. So it goes from Rp to Rm, for example, and imagine that you have this property, which is 15. So imagine that when you take the directional derivative in the direction d, you get a system which is a linear system, of course, when f is differentiable. And finding d is just a system of linear equations, okay? And finding d that solves that equation gives you a d, maybe several d's, but if you can find one which has a norm which is very small, then you will be able to prove that the solution, that there exists a solution to f of x equals 0, or f of theta equals to 0, in the neighborhood of I will do it again. Sorry. So you start from the truth. You start from theta star, okay? And around theta star, you're looking for a ball of a certain radius r, and you don't fix r, okay? Now, in that ball, you try to solve that system, okay, for all theta in that ball. You try to find a d depending on theta. So theta is in the neighborhood of theta star, okay? So you try to find a d that solves this, and if r is tuned so that you can find a solution d to that system with norm less than r, then it's all done. So it means that there exists a solution to f of theta equals 0 in a neighborhood of radius r of theta star. Okay? Sorry. So expressed in terms of the empirical risk minimization problem, you get this, of course. So you just have to compute these things. This is very straightforward, and so using this kind of notation, you end up having this system, okay, where here you have this diagonal that uses the quantity we wanted to bound in the assumption of the theorem, bound from above, and by solving that system, taking the one with the smallest norm gives you this, and expanding this expression, you obtain this. Of course, here is the matrix, diagonal matrix of the singular values, so of course you can have this bound, and that remains to there remains to have a probability bounds for this quantity. And of course, you can use well-known maximal inequalities, simplify the system, and get this at the end for the numerator, and for the denominator. For the denominator, there are very, very famous bounds provided by Verschinin, for example, in this book. At the end of the day, you end up being able to control everything, and you get that with high probability, you have this bound on the solution of that system, and this guarantees you that that this radius here is the one you should take that will control how far you have to go from the truth to go to your estimator. So that proves that you have something that solves your empirical risk minimization problem that is in that neighborhood of the truth. So you can use it, of course, for very nonlinear setups. You just need to solve, every time you want to address a sort of problem, you just need to solve a linear system. And of course, you will have a singular value to control. So how difficult would that be? This is part of the fun, but of course, Verschin's book provides a lot of bounds that can be useful for that problem. So here we find a guy which is not too far from the truth. So we can also control the prediction error with a new observation. And this can be easily done by just decomposing your problem into several steps. And that will prove that the least norm solution has prediction guarantees which are almost similar to the truth with controlled error. Okay, so you define by two steps a guy that is minimum in norm and which is able to reproduce the estimator through X, and you do the same with the additional data X plus 1, and then you expand this, and of course this is equal to 0 because this guy have the same value when passed through X with the concatenation of the last data point, and this you know it because you can control it from the previous theorem. So that remains, there only remains to control this, and the remainder of the proof is just about controlling this, which is not too difficult. Okay, and so with these tools you can try and address different problems. So you can also try and understand the lasso or various other problems which are regularized. You can try and understand the networks with one hidden layer, which is an easy task, which is quite a nightmare, but you can write the system and you can will end up finding something. And in the case of deep neural networks, maybe you can do something less general, but which is fun to do. So if you make the assumption that the dimensionality is this, so we can define the intrinsic dimensionality of the data set, which is new, which can be computed by several methods. There's been a lot of work, I think, some years ago about this. And the intrinsic dimensionality is a concept I will not delve into too much, but it guarantees that that points are well separated from each other with a certain probability. And for instance, this is a very interesting notion. There is a very nice paper by Hein and Audibert where they study the dimensionality of the MNIST, for example, data set, and they show that it's around 20. So the idea is that when you think about data as data over a manifold, then the dimensionality is, of course, exponential to be much less than what you think, and we should try and leverage this. There is a version of Neuberger's theorem which applies to Banach spaces as well, and it's exactly the same principle. So what you can do is try to avoid and address the true problem of studying deep neural networks. What you can do is decompose the problem and cheat a little bit. So you can try and solve the problem in a Sobolev space, for example. You try to minimize the empirical risk in a Sobolev space. It means that you linearize your problem, okay? And then, of course, when you try to do this, since you have only a finite number of observations, you have a kernel which is infinite dimensional, and you will be able, using Neuberger's method, to find someone in that kernel, someone in that affine space, that will be very close to the truth. And by doing this, you guarantee that there is a guy that has nice generalization properties, but you don't know if it's a deep neural network, of course, or not. But you have approximation results that guarantee that this guy can be very well approximated by a deep neural network. So by just the triangular inequality, you can prove that there is a guy which is a deep neural network that almost satisfies, that almost minimizes the empirical risk, and that has very nice generalization guarantees. So for this, you just apply Neuberger's method in the functional space. You compute the directional derivative, and you do it twice. You obtain this equation, and we'll solve that equation. And you'll see, of course, that in that setting, it's very easy. You define the bump function like this, which is something that you all know. And you have this theorem, which says that if your initial function defined on 0, 1 power d is kappa times differentiable and satisfies this, so it's a multiplicative constant in case it's not satisfied, so for all the derivatives. And if you have any estimator of f star available, what you can prove is that you can do your distance to this guy. There exists a deep neural network which, with distance to this guy, is very small, in fact. So this can be made very small, despite the horrible presentation of this formula. So it can be made very small using large width and large depth in order to control this term. And it says that the deep neural network you're going to find has the same prediction error, well, has the same estimation quality as your estimator. So this formula says that you'll always be able, whatever estimator you're going to provide, by using Neuberger's method, you can always find someone which will minimize the empirical risk and which will be approximated by a deep neural network as finely as you like. So, this network has width and depth which are of the order beta width and beta depth up to log terms, and with these multiplicative factors depending on the dimensions and the number of derivatives that you think your solution will have. So the proof is very easy. So you first solve it in the Sobolev space, and then you approximate the solution. And there is a very nice theorem by Hon and Yang that provides you all the details, and all the constants are explicit. So there is nothing under the carpet if you use that theorem. So that's it. When you solve the Neuberger problem, you realize quickly that, in fact, what you have to do is to find interpolators for the noise. Okay, so the solution will be H. We were calling it D in the finite dimensional setup. Here it's going to be H, and it has to interpolate the noise. So of course, what you're going to do is to use bump functions with a window size sigma, and this will interpolate the noise. And this is something that you can also see in several papers on the same topic. Find things that interpolate the noise only locally around the observation points, and which is very smooth outside this local neighborhood. And then you just do the computations. It's easy to find a bound on H depending on the noise, and then you use this. You plug this into the computations, and you find the formula I gave. Okay, so that's it for the results. what did I want to say? I think that's okay. So, so as you see, this is a very simple exercise, and this is fun. So Neuberger's method is a very nice tool. I think it can be applied to several statistical estimation problems. As you can see, it adapts also to the case where you have overparametrized settings for various models. By using this trick, you can also try and understand a little bit deep neural networks. Of course, as soon as you have another approximation result for another architecture, you can plug it into this proof. For example, if you have something about graphical neural networks, then you'll be able to plug into the proof the bound you have, and you'll be able to obtain results about your estimator. Okay, what we would like to prove now is that the minimizers that we were able to discover is in a location of the parameter space where the function, the empirical risk is flat, so that would be that would make the point for going further into that direction, because that would explain that stochastic gradient has a good probability of landing there. And this is all I think that you can prove about neural networks, because it's so highly non-convex. So if you don't prove that you have connectivity of the minimizers, of course, you will never be able to prove that it's going to land in the exact thing that you've provided. But at least if it's flat, it gives you more chances of thinking that there is a chance you can land there. So some papers one is available on the archive, and the other is going to be completed soon with the Sobolev norm. Thank you very much.
Thank you. We have time for 2 questions.
Yes?
Yeah, just by curiosity, you mentioned the fact that some people have proved the connectivity of minimizers.
Yes.
Can you elaborate on that a bit, or?
Yes, this is a paper by Sanjeev Arora and Rongji and other people. And they improve on results, I think, by Johan Bruna. And I don't remember his second author, but I could give you the appropriate.
So you mean that the set of minimizer is connected?
So it means that you can find paths which are linear, which are fine, with less than 7 segments that join minimizers, local minimizers. What are the assumptions? What did I say? 7 segments, and yes, of course. So the objective function never goes above the maximum value between both of them, plus epsilon, and epsilon depends on the characteristics of the network. So
and they have bounds on the path. Sorry? They have bounds on the length of the path.
That I don't know. I know that there is a bound on the number of segments.
Segments.
Yeah.
So the curvature.
No, it can be straight, but they have a bound which is 7 segments. So there is no notion of curvature there. There is a nice blog also by Rongji that explains all this.
Yeah, I mean curvature is the broken piece.
Yeah, if you like. Okay.
Other questions? I think we're entering the gravity field of the lunch.
Exactly. Thank you.
So let's thank the speaker again.